this set of notes, we're going to look at the concept of random variables. So a random variable is a real valued function for which the domain is the sample space. So we're going to go back to that idea of sample space that we saw last time. And a random variable y is discrete if it can only assume a finite or countably infinite number of distinct values. And so just to recall, a set of elements is countably infinite if the elements in the set can be put into one-to-one correspondence with the positive integers. And so we're going to look at a couple different examples here, and we'll talk about what the sample space is for each of these. Alright, so each of these random variables are going to be discrete. And so our first one we have here is the number y. So notice y is capitalized here. We're going to call that a random variable. And it's the number of masks distributed today at UK Chandler Hospital. So the question here is, what are the possible values? Alright, so we know we can't distribute negative mask, but it is possible that they distribute 0 mask on a particular day. They could distribute 1, 2, 3, and then keep on going. We can't really put an upper bound on that value. And so this is what we would call countably infinite. Right, the next one is the number y of pre-op bays out of 5 which do not meet HIPAA compliance at a randomly selected eye surgery center. Alright, so the maximum number that might not meet compliance would be 5, and the lowest number is 6. Is 0. So we could have 0, 1, 2, 3, 4, 5, or 6. So, not 6. 0, 1, 2, 3, 4, or 5. And so notice that this one is what we would call finite. And then the age x of a randomly selected unemployed adult to the nearest year. So if we're only considering adults, the lowest age we could have is 18. Person could be 19, all the way up to whoever the oldest living human being is. And off the top of my head, I'm not sure what that is, so let's just pick some large number. We'll say up to 115 years old. And again, this one is going to be finite. Alright, so we're going to look at probability distributions for different discrete random variables. So when working with random variables, the notation is going to be very important. Notation can help us distinguish between different types of functions and whether they're random or non-random elements. So we're going to use uppercase letters such as y to denote random variables. And typically what you see is uppercase letters towards the end of the alphabet. So you're going to see a lot of X's, Y's, W's, Z's. Whereas remember when we talked about sets, we tended to use uppercase letters towards the beginning of the alphabet. Now there's no set in stone rule here, but typically that's what you're going to see in the notation. We're going to use lowercase letters such as little y to denote a particular value that a random variable may assume. So generally what we say is whatever the capital letter we use the lowercase version of that just as a placeholder for different potential values. So for example, you'll see this down here, but just to have it on this page, we might say something like the probability that capital X equals little x is equal to, and then we're going to give some function over here on the right hand side of the equation. And that function is going to depend on that little x. So in other words, what we're saying here is little x is just a placeholder for a bunch of different values that our random variable may take. Now we can summarize a discrete random variable by giving its possible values and their corresponding probabilities. So we've got a couple definitions here. So the probability that capital Y takes the value of lowercase y, probability that y is equal to y, is defined as the sum of the probabilities of all sample points in S that are assigned the value of lowercase y. And sometimes we will denote the probability that capital Y equals lowercase y is just a lower case p given y. These mean the exact same things. When we use this notation here, it's sometimes referred to as the probability function of y, and probability functions are sometimes called probability mass functions. So this is another one of those cases. Don't get too lost in the terminology here. As with a lot of things you're going to see in statistics, we use different names to mean the exact same things, and same thing with notation. Now the reason that they're called probability mass functions is because they give probability of mass assigned to the finite or countably infinite possible values for these discrete random variables. And we'll see an example of that here in a second. The probability distribution for discrete random variable, capital Y is a graph, table, or formula that specifies the probability P of y for all y. Now one thing to notice is since this does represent a probability, then of course it has to be greater than or equal to 0. Like we saw when we talked about probability, we can't have negative probabilities, and also for that same reason, this cannot be greater than 1 either, because we know that probabilities are restricted between 0 and 1. So here are those probabilities, and this is exactly what I was saying. Notice since P of y is a probability, it is restricted between 0 and 1, including 0 and 1. And then also, if we sum up P of y for all the possible values of y that have non-zero probability, this sum is going to be equal to 1. And so one way to think of this is we're summing over the sample space of y, and if we sum up over the sample space, we have to add up all of the probabilities. Alright, so for example, suppose that the American Heart Association claims that only 10% of adults over the age of 50 in the United States can pass the minimum physical fitness standards. Suppose we select 4 adults at random who are over the age of 50 and give them a fitness test. Let y be the number who pass. Find the probability distribution of capital Y. So notice here that capital Y is going to be the number that pass. And this is going to be out of 4. So if we look at the potential values that capital Y can take, notice that we could have 0, 1, 2, 3, or 4 pass. So one way that we could summarize the possible values that the random variable could take is in a table. So it could take the value 0, 1, 2, 3, or 4. And then next to each of the potential values, we need to give the probability that the random variable takes that value. So let's see how we could calculate this. So if we want to find the probability that y is equal to 0, and notice this is the same thing as lowercase p at 0. What this would mean is that no one passes. So up here, notice that we have only 10% of adults over the age of 50 can pass the minimum physical fitness standards. So if 0 people pass, and we know that there's a 90% chance of not passing, what this means is that the first person didn't pass, the second person didn't pass, the third person didn't pass, and the fourth person did not pass. And notice here the reason that I'm able to do the multiplication is I am going to assume that each of those randomly selected adults over the age of 50 are independent of one another. So notice this probability is 0.6561. Similarly, we could find the probability that all 4 of them pass. And here again, there's only a 10% chance of passing. So for the first person, there's a 10% chance, the second person, the third person, and the fourth person. So again, assuming independence here. Okay. Now we have to be a little bit more careful when we calculate the probabilities for 1, 2, or 3. And the reason for that is we have to find the different ways in which these can occur. So, for example, if I want to find the probability that only one person passes, notice it could be that the first person, the second person, the third person, or the fourth person is the person who passes. So if it's the first person who passes, I'm going to have 0.1, and then the other 3 fail. Or it could be the second person is the one who passes. Or it could be the third person. Or it could be the last person. So, in order to find this probability, I need to add up all of these possibilities. And if you put that in your calculator, you'll find that this is equal to 0.2916. And then we would do something very similar to find the probability that 2 pass or 3 pass. I'm just going to go ahead and give you what those values are. And it ends up that this actually has a special name. It's called a binomial. So just have that as a side note, and here in a little bit, later on in the notes, we're going to actually learn about the binomial distribution. But for right now, let's look at what we've got here. Notice we're looking at the number of people who pass out of 4. And so the options we have are 0, 1, 2, 3, and 4, and we have their corresponding probabilities. So this table right here defines the probability distribution of y. We have all of the potential values for y and their corresponding probabilities. Now, one thing to notice is that in order to be a valid probability distribution, notice we've got these two properties up at the top. All of the probabilities have to be between 0 and 1. So if we come down to our table, notice that all of our probabilities, so remember these are all of our probabilities, they are between 0 and 1, so that is satisfied. And then we also need to double check that they all sum to 1. And if you add all of these up, they do sum to 1. So we have a valid probability distribution. All right, so here's another example. In a study of military personnel, participants were asked to complete surveys that ask about health behaviors and health states. Participants were asked to rate their health on a continuum from poor, which is represented by y is equal to 1, to excellent, y is equal to 5. And so we have this following discrete probability distribution. And one correction here, and I'll correct this in your notes, this capital Y, that should be a lowercase y. All right. So notice here, if we're rating on a scale from 1 to 5, there are 5 different potential answers that a person could have. Below this, we have the probability of each of those potential answers. So notice that each of the probabilities are between 0 and 1, and if we add those up, they do add to 1. So we do have a valid probability distribution here. So let's use this probability distribution to help us find some different probabilities. So the first one says, find the probability that a randomly selected participant reports a score less than 3. So here what we're looking for is the probability that our random variable y is less than 3. Now if we look up at our table here, notice the only two values that are less than 3 are 1 and 2. So this is equal to the probability that y is equal to 1 plus the probability that y is equal to 2. Further, notice that y being equal to 1 or y being equal to 2, these are disjoint. There's no way that a person can score both. So this is why we're able to add these probabilities together. All right. So the next one says, what is the probability that a randomly selected participant reports a score of at least 4? So this means the smallest that y can be is 4. And so if we look here, again, scores are restricted between 1 and 5. So this is equal to the probability that y is equal to 4 plus the probability that y is equal to 5. And so we can solve this very similar to what we did up above. And one last one here, we want to find the probability that y is less than or equal to 2 or y is greater than 4. So again, we could just list out the different probabilities. And going back up to our distribution. And then again, we can put this in our calculator. All right. So here we can see, when we have a relatively small probability distribution, calculating the probabilities is fairly straightforward. And one thing to notice here is, remember we call this the probability mass function. So notice that y can only take 5 values. And the reason we call it a probability mass function is because the individual values have an actual probability associated with them. Now, soon we'll talk about continuous random variables, and what you'll find is for continuous random variables, that is not the case. All right, so let's talk about the expected value of a random variable and functions of a random variable. So the probability distribution for a random variable is a theoretical model for the empirical distribution of data associated with the real population. If the model is accurate, then the theoretical and empirical distributions are equal. All right, so, and this shouldn't say in this chapter, it's just in this note set, we're going to attempt to find the mean and variance of the random variable. Thereby we are acquiring parameters for probability distributions. So here's a definition. Let y be a discrete random variable with probability function p of y. The mean or expected value of y is given by the following. All right, so looking at our formula here, essentially what the mean or expected value is it's a weighted average, where the weights are determined by the probability of each of the possible values. So notice what we've got here. We're going to sum over y. So little y, those are all the possible values that y can take. And then p of y is the probability those values occur. So one way to think of this is if I had a random variable, and let's say this random variable only took 2 values, 0 and 1,000,000. Well, let's say it takes 0 1% of the time and 1,000,000 99% of the time. What the expected value does is it says on average what do we expect to see. Well, if 99% of the time I get 1,000,000, on average I'm going to expect something close to 1,000,000. I'm not going to see the 0 very often. So this is why when we compute the expected value for the discrete random variables, we weight by the probability that the different values occur. So let's go back to our example that we had earlier. And again, this is the study of the military personnel. So if we wanted to find the expected value of y, again, what we're going to do is we're going to look at each of the possible values that y can take, and we're going to weight that by the probability it takes that value. So here, to find the expected value of y, for each of the values, so for example, starting with 1, we're going to take 1 and multiply it by the probability that 1 occurs. Add to that 2 times the probability that 2 occurs, 3 times the probability of 3, and so on. Okay, and so take a moment, go ahead and put that in your calculator. I get 3.41. Now, one thing to notice here, our expected value is not one of the potential values that y can take, and that's perfectly fine. A lot of times the expected value will not actually be in the sample space. And again, this is because we're thinking about what's occurring on average. This is just like you hear the saying that on average households have 2.4 children. Of course you can't have 2.4 children, but you can have that on average. So keep that in mind, as you see different expected values. If the expected value is not part of the sample space, that is perfectly fine. In addition to the expected value, we can also talk about the variance of a random variable. And so the variance is defined as follows. It is an expected value, but instead of being the expected value of y, what we're looking at here is we're looking at the square difference between the different values of y and the expected value, or the average. This is actually your standard definition of variance that you've seen back in your intro stat class, because if you think about how variance is calculated when you look at a data set, essentially what you do is for each of the elements in the data set, you take the difference between that value and the mean of the data set, and you square it, and you take an average of that. Well, we're going to do the exact same thing here, but instead of taking the average of that squared difference, it's going to be a weighted average again, where those weights are determined by the probabilities of the different values that y can take. And so again, looking at our example, let's calculate the variance and the standard deviation of this random variable. Now on the previous page, we just saw that the expected value, I'm not using x's, we're using y's. We just saw that the expected value of y was equal to 3.14. So we're going to use the exact same process that we just used to calculate the expected value. Same process we used to calculate the expected value, but now we're going to do the variance. So here, the variance of y is still going to be a weighted average, but instead of weighting based on the individual values of y, what we're going to do is we're going to take each of those values, we're going to subtract off the mean, square it, and multiply by the probability of that value. So it's still a type of weighted average. So again, if you want to pause this for just a second, go ahead and put this in your calculator and see what you get. And I just realized that I made a mistake when I wrote this down. These should all be 3.41. So if you put that in your calculator the correct way, we should find the variance is equal to 0.7139. And then remember, the standard deviation is always just the square root of the variance. So then our standard deviation of y, and we could denote that as just sigma, or square root of the variance of y, is equal to 0.8449 rounded. All right, so here we have that example from earlier with the American Heart Association, and here is that distribution that we found earlier. So I'd like you to pause the video here and see if you can find the expected number of adults who will pass the fitness test, and then also see if you can find the variance. And then when you come back, we can double check those values and see if you got the same thing that I got. All right, you should have gotten that the expected value of y, and we could also denote that using mu, is equal to 0.4, and that the variance is equal to 0.36. Now, as you've probably noticed, computing this expected value using the sums can kind of be a pain. So what we're going to look at next are a couple theorems, and these theorems actually help us find a shortcut formula to the expected value. All right, so here are those theorems, and again, we're not going to prove anything in this course, but these are good theorems to know. So the first one says if y is a discrete random variable with probability function p of y and g of y be a real valued function of y, then the expected value of y is as follows. And you actually already saw this. So notice here we're interested in the expected value of g of y. Well, that is just, again, going to be a weighted average where we weight each of the outcomes of g of y by the probability of that y value. So same thing that we just did when we calculated the variance, because that's really what we were doing. We were taking the expected value of a function of y. Let y be a discrete random variable with probability function p of y and c be a constant. Then the expected value of the constant is always equal to the constant, and that will always hold. And the reason for that is a constant is not random. So you can't take the expected value of it. It's just the value that it is. And the next one kind of combines the two up above. It says if we have the expected value of a constant times some function of y, then we can just bring the constant outside of the expected value. Here, if y is a discrete random variable with probability function p of y, and now let's say that we have several different functions of y, then if we look at the expected value of the sums of those functions, then that is equal to the sum of the expected value of the functions. And then this brings us to our shortcut formula. So let y be a discrete random variable with probability function p of y and mu equal to the expected value of y. Then notice the variance of y is equal to the expected value of y squared minus the expected value of y squared. And so we're going to use that formula here. So just to help us out, so we've got this on the same page, let's write that formula here at the top. It doesn't really matter if you use the curved or the brackets, but just to make it consistent for how I've written this. There we go. Okay, so we're going to find that variance, but now we're going to use our shortcut formula. So in order to use this formula, we are going to need the expected value of y squared. And again, notice that this is going to be a weighted average of y squared. So here, to find this value, you would take 0 squared times its probability, 1 squared times its probability, plus 2 squared times the probability, plus 3 squared times the probability, plus 4 squared times the probability. And if you did do that, you should find that's equal to 0.52. And we're already given that the expected value of y is 0.4. That's what we found early on. So now the variance of y is equal to, well, the expected value of y squared is 0.52 minus 0.4 squared. And then to find the standard deviation, remember the standard deviation is equal to the square root of the variance. And so this way is usually much easier to calculate than using the longer formula. Oh. So there's the standard deviation right there. All right, one more example. So a certain manufacturing company produces 1,000 medical devices each day. Usually 90% of the devices are not defective. Only these can be sold. Let Y be the number of non-defective devices that are produced in a day, and suppose the daily total daily profit for the company is given by this formula. So notice that this is a formula, which is a function of the random variable Y. So we want to find the expected daily profit using the fact that the average number of non-defective devices each day is 90 and the variance is 90. So let's see how we could do this. Notice they're giving us that mu is equal to 900 and that sigma squared is equal to 90. Now we can actually use our shortcut formula to help us out. Notice if we want the expected profit, that's going to be equal to the expected value of 5y plus y squared minus 700,000. And using one of those formulas that we had earlier on, we can see that this is equal to the expected value of 5y plus the expected value of y squared minus the expected value of 700,000. And then using one of the other theorems, remember if we have a constant, we can bring the constant outside of the expected value. And then the expected value of a constant is just a constant. Alright, so we already have the expected value of y, that is mu, but the piece we don't have is that expected value of y squared. And so that's where the variance can help us out using that shortcut formula. So here's our trick. Remember that the variance sigma squared is equal to the expected value of y squared minus the expected value of y squared. Well, we know what this value is and we know what this value is, so therefore we know that the expected value of y squared is equal to the variance plus mu squared, or the expected value of y squared. And we have these values. So the variance is 90 plus 900 squared. So therefore, substituting in, we have the expected profit is equal to 5 times 900, or 5 times the expected value of y, plus 810,090 minus 700,000. Which gives us an expected profit of $114,590. And this is going to conclude this note set.